In this lesson we're going to continue to look at specific heat capacity. This time we're going to have a look at some specific heat capacity problems or calculations. So we remember that from the previous lesson, the specific heat capacity of a substance is the heat required to raise the temperature of 1 kilogram of that substance by 1 degree Celsius. We can write this in the form of a formula. We say that C, that's the specific heat capacity, again, just repeating, is the heat required to raise 1 kilogram of the substance by a temperature change of 1 degrees Celsius. And what we can say is that this is a property of substances and that each substance has a different specific heat capacity. So for example, let's say that we have a litre of water, that's 1 kilogram of water, and a kilogram of copper. Okay, a block of copper that weighs 1 kilogram. Okay, both have the same mass, and we want to find out how much heat is required to produce a temperature change of 1 degree Celsius in the kilogram of copper and in the kilogram of water. Before we do that, we need to know the specific heat capacities of the water and the copper. Now we can Google that, or we can go to a reference book to find the information we require. We find out that the specific heat capacity of water actually is very, very high indeed. It's 4,186 joules per kilogram per degree Celsius. So water is a substance with one of the highest specific heat capacities, whereas that of copper is 385 joules per kilogram per degree Celsius. Just make a note of the units here. We've got joules per kilogram per degree Celsius. That comes out of the formula. We've got heat here, that's joules divided by delta T divided by M, that's kilograms, divided by delta T, that's a change in temperature, so that's degrees Celsius. Okay, so that can also be written as joules per kilogram per degrees Celsius. Okay, so another way of writing that. Okay, so what we want to find out then is how much heat is required to raise the temperature of the water by 1 degrees Celsius, and compare that with the amount of heat required to raise the temperature of the copper by 1 degree Celsius. Okay, so just rearranging this equation, Q equals, and now specific heat capacity, which is different in each case, times delta T, the change in temperature, times the mass. So in the case of water, the heat required in this case is 4186 times the change in temperature is 1. We specified that, times the mass, which is 1 kilogram, which is equal to 4,186 joules, which is what you'd expect. Whereas the case of the copper, that's going to be 385, the specific heat capacity for copper, 385 multiplied by 1 multiplied by 1, which is equal to 385 joules. So clearly, it is much easier to raise the temperature of copper than water. That's to say, to raise the temperature of 1 kilogram of water by 1 degree Celsius requires over 10 times more heat than to raise the temperature of 1 kilogram of copper by 1 degree Celsius. So let's just have a look at a typical type of problem we might find, for example, in a GCSE physics paper covering specific heat. So you may be given some sort of problem like this. You've got a block of iron, okay, and you're told that the specific heat capacity of iron is 444 joules per kilogram per degree Celsius, and you're told you've got 480 grams of iron. And inside the iron there's a heater which is going to supply, for example in this particular case, let's say 2,500 joules of heat to the block, and you're told that a student sets this up and he wants to predict what temperature change will occur in the block. Yeah. Okay, so he's going to use, or she is going to use, the formula. Again, this is the one you remember: C equals Q divided by delta T times M for mass. And so you're asked here, what is his prediction of the resulting temperature change? Okay, based on the information that he's got at hand. So you rearrange the formula and you write delta T is equal to Q over C times M. You plug in the values. Now here, typically this is always going to happen, that an examiner will give you the mass of the block in grams to try and trick you, and what you got to remember is that the unit in this formula is kilograms. You cannot use grams, so you've got to change that to kilograms. So your value for the mass is 0.48 kilograms. You divide that by 1,000 to change it to kilograms, and you plug the values in. Okay, so you got 2,500 divided by 444 times 0.48, and that comes out as 11.73 degrees Celsius. And you are then told that when the student performed the experiment, he found out that the temperature change was in fact only delta T equals 8 degrees Celsius. And then you are asked to explain that and to explain what the pupil or student did wrong. And you realise that what he hasn't done is he hasn't taken into account that heat will be lost from the block to the surroundings as the heater heats it up. The heat is being transferred from the immersion heater to the iron block, but it is then escaping from the block to the surroundings via, you may be asked, how does this happen? It could be via conduction through contact with the floor, for example, or table, or it could be through convection or through radiation, etc. But heat is being lost. And so the question is then, how could he have done the experiment better? How could he have improved the experiment? And you then state that he should have used insulation to stop this heat escaping. Okay, so now, for example, we've got some insulation. The iron is in a polystyrene block, for example, and that's stopping the heat from escaping. So now he's going to get much nearer to this 11.73 degrees Celsius when he does the experiment properly. Now, what is almost certain in this type of problem is, especially where you've got an immersion heater, is that you probably won't be told specifically, as I have done, the amount of heat that's applied to the block, but you probably be asked to calculate it through your knowledge of power transfer and electric circuits. What I mean is this: what you'll be told is, rather than telling you explicitly that the heat supplied to the iron block was 2,500 joules, let's remove that, they may say in the question that the heater was supplied with a current equal to 3 amps at a voltage V equal to 12 volts during a period of time of 3 minutes. And then what you've got to do is you've got to remember your formula for electrical power transfer in a circuit. So we remember that the power is equal to the energy transferred per unit time, per second. Therefore, the energy transferred, which is what we're interested in, is equal to the power times the total time through which that power is operating. And then remembering that the power is equal to the voltage multiplied by the current. So you plug that into that energy transfer equation, which gives you E equals V times I times T. T is in seconds. Sorry, that was 1 minute. They may well, again, just to trick you, they may give you the time in minutes, and you've got to change that to seconds, which you know is 60 seconds. And so that gives you 12 times 3 times 60, which comes out as 2160 joules. Okay, so that is your value of Q that is being transferred into the block. Okay, Q will be equal to 2160 joules, and then you will then go on to the next step, which will be to use the specific heat equation to work out the resulting change in temperature.